Today we have as our guest Yannis Liodakis. He's at University of Turku and the Finnish Centre for Astronomy with the he got his PhD from the University of Crete, and then he was a postdoc at Stanford working with Roger Romani, and he's done a lot of work in population studies of active galactic nuclei, and also he has studied the prospects to learn more about relativistic jets using X-ray polarization. And he's one of the leaders of the task force that's going to be looking at high-frequency peak lags with IXPE, which is an X-ray polarimeter that's going to be launching soon in December and starting to run beginning of next year. So Yannis, whenever you're ready, you can go ahead.
Sure. So hello, everyone. Thank you very much for the introduction, and thank you particularly for the invitation. I was hoping before the pandemic that I could do a tour of the East Coast and visit you, but that was not possible. Maybe sometime in the future after IXP's launch, we'll have more exciting stuff to tell you. But still, I'm going to try today to convince you that polarization is a great way to learn about supermassive black holes and their jets. So just for a brief introduction, we now at least think we know that every or most of the galaxies in the universe have a supermassive black hole in the center. And our most compelling evidence comes, of course, from our own galaxy. And what you see in this animation are basically orbits of stars around a very massive dark object in the center of the Milky Way, which we call Sagittarius A star, and is what we think the black hole in our own galaxy. By massive here, we mean something around a million or a few million the mass of our own sun. So Sagittarius A star is relatively a quiescent black hole. It's not really doing much. There are other black holes in the universe that are very energetic and very active and form what we call active galactic nuclei, which are very, very compact and very bright objects. Now, for reasons we don't fully understand yet, there is a small fraction of this AGN that launch very collimated and often highly relativistic streams of plasma that we call jets. So this is how an active galactic nucleus with a jet would look like. For historical reasons, we call those radio galaxies. And what you see here is the bright spot in the middle, which is the AGN. And then you have the thin lines that are coming left and right from the AGN, which are the jets that I just told you about. And then at the end, you have these giant bubbles, which we call the lobes of the jet. And this is where basically the jet terminates and it started mixing with the intergalactic medium and it's forming shocks. Now, if you focus on the bright spot in the middle, this is what it will look like. This is from, of course, radio imaging. And the bright spot you see, this is what we call the core of the radio jet. This is what we think is the base of the jet, although there are alternative theories. And what's coming out towards the right, that's the main jet. The similar but much dimmer feature that you see on the other side, we call that the counter core, and that's the counter jet. And somewhere between core and counter core is the supermassive black hole that is powering both of those jets. Now imagine you're an observer on the far side of the universe, and the jet is now not on the plane of the sky, as you see in this example, but it's actually coming towards your line of sight. So it's basically aligned with the observer. And this is, when that happens, we consider that to be a subclass of this AGN with jets, which we call Blazars. And this is how Blazars look like. And of course, you will notice that we don't no longer have two jets. We have just one bright spot. We still call that the core of the jet, although it doesn't really correspond to the base anymore. And we get a little bit of the jet because these are, of course, not perfectly aligned with our line of sight. They're just a little bit off axis. So, of course, now that we lost all the structure, the only way to study these sources is to look at their multi-wavelength emission and try to make some sense out of what we're observing. And there's been a lot of effort over the years put into that, and people have come up with many different models of how blazars look inside. I'm showing you here just one of these models, which I would say is the most popular one. So what you see here is the black hole. This is we call an accretion disk. It's basically how the black hole is being fed gas, and then a jet is launched, and it goes through what we call the broadline region. This is basically clouds of gas that are orbiting the black hole, and this is where we think the optical spectral lines that we see in the sources come from. Then the jet is collimated, is accelerated until it reaches what we call the core of the jet, or what we think is the core of the jet. And there you have, this is what we consider to be either some standing shock or, according to at least some magnetohydrodynamic simulations, this is the first we call emission shock of the flow, where you have a lot of particle acceleration and a lot of high energy emission. And then once you pass that, now you're in the parsec scales, and you see more and more of the radio jets I've been showing you all this time. So then if you take a look at M87, this is the source that gave us the first image of the black hole, of course. M87 is not really a radio galaxy, but it's not really a blazar either. It's something in between. We often call this misaligned AGN. And what you see in the images below, which are in radio, optical, and X-rays, basically the emission profile is a little bit more complicated than this kind of simple model, but a lot of the structure is there. And in fact, if you try to study this structure, and people have, they found that as you move away from the black hole, the jet seems to be parabolic, which again, according to the simulations, I told you is where jet acceleration is favored, basically, until it reaches what we call the Bondi radius, which is basically the sphere of gravitational influence of the black hole, and at which point it transitions to a conical geometry, which no longer favors acceleration, which all of this, of course, matches very well with the model I just described. Now, why this transition happens at the Bondi radius? We don't know. It might be coincidental, but what we do know is that this kind of transition geometry is by no means unique to M87. There are now many known nearby radio galaxies where we could resolve the jets that they also seem to have a similar transition kind of geometry. So we're, structure-wise, we're getting somewhere for sure. But what happens with the emission? And that's a lot of where my talk will focus today. So what I'm showing you here is what we call the spectral energy distribution, just brightness versus frequency for a bunch of different blazars. They all have this two-hump shape. As you can see, there are a bit of variations between sources, but generally the two-hump shape is the dominant shape that they have. So, and as you can see, it spans from radio all the way to very high energy, even TV gamma rays. So the first bump that you see there goes from radio up to X-rays. That's caused by synchrotron radiation from relativistic electrons that have been accelerated in the magnetic field of the jet. We have a few evidence in favor of that, but our maybe strongest ones come from polarization. Now, on laboratories on Earth, we make polarized light by putting filters in front of a light source. Nature kind of does this using magnetic fields. So in this particular case, the electrons travel along the magnetic field lines, which gives them a preferred direction of emission, and that gives rise to polarized light. And we have observed blazars to be as high as 45% polarized. Now, again, in terms of physics laboratories, this is not a lot, but in terms of astrophysical context, this is basically as high as it can get. There are maybe a couple of other ways that you can get this level of polarization other than synchrotron radiation. Of course, blazars are not always 45% polarized. These are kind of extreme cases. The most common level is around, let's say, 10%, and it's varying stochastically, typically over time. So what I'm showing you here is one example of a blazar that we've been studying with a group I'm working with called Optical. So on the top panel, you see the polarization degree. The middle panel has the polarization angle, so basically the orientation of the polarization plane, and the bottom panel is the brightness in the optical. So while typically you would expect random fluctuations in the polarization for blazars, there are moments in time, for a few of them at least, we don't know if all of them do this, where we see coherent changes of the polarization angle towards one direction. And we call those EVPA rotations. So basically, the jet is doing something stochastically, and suddenly it stops, and it moves the polarization plane towards one direction. This is what you see with marked with red points. And then after it's done with its rotation, it goes back to doing things stochastically. Now, this is something you would not normally expect from a jet. And it has puzzled people a lot whether what we're seeing is actually real. So whether there's actually something changing in your jet, or we're just looking some random walk motion where you just, it happened that the polarization angle would move towards some direction for some time. So we built, basically, Optical was built in trying to figure out what was going on with these events. And among our first results was to discover that the jets that make gamma rays seem to be systematically more polarized than the jets that don't make gamma rays. We also found that where the peak of the synchrotron emission is correlates with how polarized you expect the sources to be. Both of these things are not really obvious. And I would say our most striking result was when we compared the arrival of gamma ray flares with these EVPA rotations. And we found that every time we detected the rotation, we also saw a flare come along with it, which is statistically very unlikely to happen by chance. Which means basically that these are real events, or at least some of them have to be real. They cannot all be completely random. What is causing them is a different story. And we try to answer that in a paper we published recently, where we studied one particular source. It's called C3454.3. Is a very active source. And what really caught our eye was that it was going through a period of extended quiescence, which is very atypical for that source. So this happened around the end of 2013, and you can see that the source is not really doing much. And then it had this very nice, clean, I would say, one peak flare, and then went back to quiescence. What is particularly interesting is that it also had a flare in polarization. So in just a few days, it went from being 5% polarized all the way up to 30, and then back down to 5. And then it went about its business of randomly fluctuating. And we also saw this weird behavior in the EVPA, where it goes towards one direction until the flare maximum, and then flips direction and goes the other way. Which, of course, it also could be coincidental, but it just seemed weird to be at the time. But after this quiescence, in just a few months, the source had another outburst, which we again can see throughout the electromagnetic spectrum. And but this time, this outburst is a little bit more complicated. We don't have just a single peak now. Now there are like 3 peaks. They all seem to align with each other. So even in from gamma rays to infrared, they seem everything to match. we also see a flare in polarization, but now it doesn't align with the other flares, which is also kind of intriguing. It's actually somewhere in between two flares. And it goes up to 20% from around a little bit over 5 now. But then within 2 days, it drops down to 0 and then back up 10% and just goes about its business. And at the time we saw this 20% drop in polarization, we also saw this beautiful 230-degree rotation of the polarization plane. So that cannot exactly be coincidental. So it got us thinking, and we tried to get more and more data and try to understand what was really going on. And at first, we thought, as you might be thinking right now, that these two events are just completely separate things. Something completely different happened in the source, which we don't know about. But it turns out that we were actually looking at the same thing, which just manifested itself in a very different way. And our most compelling evidence actually came from radio observations. This is kind of a busy plot, but don't worry, I'll walk you through it. So basically, there's a group at the Boston University that is monitoring these sources with very long baseline interferometry. This is where you have a bunch of radio antennas all synchronized together, forming a very big kind of radio telescope, which give us resolution which is orders of magnitude higher than any other telescope we have, basically. And that really allows you to kind of resolve the jets and see structure and see also things moving in the jet. So every little arrow you see there is basically something that they have detected on their radio maps, and they've calculated what was the distance from the core, which in terms of radio astronomy, now the core is defined as the brightest pixel in your radio image, basically, versus time. So what is interesting here is this component C, which should be stationary, and it has been stationary for many years. But now they saw that around 2013, there started to be kind of an inward motion of that component. Basically, that means that that thing was falling towards the black hole, which doesn't really make sense since everything in the jet is moving outwards. What was really happening is that this is a completely an observational artifact. The reality is that something was moving out of the core, but it was under the resolution of the telescope. So you cannot really distinguish it from the core, which makes the centroid of the emission move slightly forward. And because you're measuring everything with respect to the peak of your, the peak pixel, we'll see this stationary features move kind of inwards. So when this flare happened that I just told you about, which was in 2014, they saw also the ejection of K14, which is a component that was clearly separated from the core. And when they saw that, they also saw that the component C was going back to its original position. So what we really think is happening is that the source was in quiescence until 2013, where there was something, we don't know exactly where, but it started propagating in the jet. We hypothesized this is a shock. And as it was moving down, it met some kink, some bend in the jet. We don't know exactly, but what we do know is that it changed its orientation towards the observer. Think of it as a lighthouse effect, basically. When the light from the lighthouse kind of sweeps your line of sight, there is a moment in time where it becomes very bright, and then it goes back. In the same way, it was in quiescent, became very bright, giving us this flare, and then went back to quiescent, and then continued its travel down the jet for just a couple of more months, when it crashed into the stationary shock we call the core, and basically we saw this outburst. So we were able, kind of for the first time, to track something moving in the jet behind the core, and we're able to kind of relate two very different events to the same mechanism. And of course, we now know that shock-shock interaction is at least one of the ways that you can make this rotations of the EVPA. And in this case, is basically, think of it as having two polarized components with different polarization orientation. If you do the math, while these two components change their contribution to the total emission, that would lead to depolarization if they come at exactly the right polarization angle. So everything seemed to match fairly well. So I'll be moving on to slightly higher energy stuff. So I'll pause here and ask if there are any questions so far. I cannot see the chat in case somebody.
Yeah. No, I think I'm looking at the chat. There's no questions, and we don't have questions here in the room. So yeah, you can go ahead.
Okay. Move on. So what happens with the high energy emission? And this is something that is kind of a hot topic nowadays, and it's something that we really don't know. So this bump is basically starting from X-rays going all the way to TV. And there are two families of processes that we think of while we try to explain this emission. One's what we call leptonic processes. This is basically when electrons are dominating the radiative output of your jet. And the most relevant process here is what we call inverse Compton scattering. Basically, electrons move down the jet and they see some target photon field. That could be from the electrons themselves. So we call that synchrotron self-Compton, or it could be some external source of photons, from the accretion disk, broadline region, or somewhere else, in which case we call that external Compton. The other family of processes, we call it hadronic. This is where now protons dominate the radiative output, and protons can either be directly accelerated, in which case they make proton synchrotron, or they interact with other protons or other photons, they make pions, and then pions decay to a bunch of different particles, but also gamma rays. So the typical way we try to figure out which is the dominant process is through what we call SED modeling. So basically you gather a bunch of data, you build your SED, and then you make models trying to fit that SED and trying to figure out which model works best. But as you can see in this example, you have two different models giving you a very similar fit to the data. It's not that we don't learn a lot from SED modeling, it's just it hasn't really been conclusive and differentiating between these processes. So you can imagine how excited everybody was when about 4 years ago now, IceCube, which is a neutrino observatory in the South Pole, detected a very high energy, a few hundred TV neutrino coming from the direction of a blazar, which is called TXS0506+056. So people got super excited because this is another kind of probe of testing this emission processes. And this is where it really gets kind of interesting, I would say. So if you look at the left plot, this is a leptonic model which fits the data very well. But you can ask any physicist and they will tell you that electrons don't make neutrinos. Then on the right-hand side, you have a hadronic model, which you can make as many neutrinos as you like, but you also will overproduce the X-ray and gamma ray emission of the source. So that doesn't really work either. And since then, there are basically now tens, it could be even hundreds of different models with different geometries, different configurations, trying to explain both the electromagnetic emission, but also the particle emission we saw from the source, or at least we think we saw from the source. So I'm just giving you a few examples here, but as I said, there are tens of different models out there. So it's kind of fair to say that we haven't really, we basically have more questions now than answers since that neutrino event. So we thought we should be going a different way than the rest of the people and leave them do all the SED modeling. So we thought we should look for other tests of this emission process. And there is a clear prediction in these leptonic models where you expect to have a correlation between the low energies, and the most common is optical basically, and the higher energies, which are gamma rays. So basically you need something to be upscattered through inverse Compton scattering to make gamma rays. So, and this is kind of a signal that we can look for. So if you have two light curves, then which basically how the brightness of the source changes over time, you can try to align them and see where your correlation will be maximum, correlation coefficient. So we gathered data for about 178 sources, which is kind of the biggest sample that has everyone looked at in optical and gamma rays, and we managed to find the correlation to 121 of those, which you see on the right. So basically this shows the statistical significance of the correlation versus the time lag, which is basically how much we needed to shift one light curve to match the other. And as you can see, there is a very strong preference for simultaneous variations. Of course, not all our correlation coefficients are above 3 sigma, which is, by the way, plenty for astrophysics. And that doesn't mean that we don't have a correlation. Basically means that there are a lot of other things happening, which is very common in astrophysical system. So basically you have some random fluctuations from the jet. You might have an accretion disk that doesn't really care what the jet is doing, and that kind of adds noise to your light curve, which is uncorrelated, and that brings your statistical significance down. But there is one other thing which is very interesting, and is what we call orphan flares. This is basically when we have an outburst in gamma rays, for example, but we don't see a counterpart in the optical. So now that we knew how to align the light curves, it would just takes a little bit of modeling to try and match the flares we see in one band with the flares we see in another. And by doing so, we found that about 20% or 21% of the gamma ray events are orphan. So there is no optical, nothing happening in the optical during these gamma ray flares. Now to put that into context, that translates to about 1 flare per source every 3 years. So it's not really that much, but at least according to the very simple leptonic models, those should not exist at all. Of course, you can have a lot more complicated models, but it's just easier if you have just a bit of protons that will do something occasionally in your jet. So the conclusion we're coming to is that leptonic processes seem to dominate the overall emission, but there is still some room for hadronic emission. So we clearly need kind of to do better. And again, polarization now at the high energies could provide the solution. So as you see in the bottom panel, this is another fit to the SED where, again, 2 very different models, or now it's a few different models, can give you a very similar fit to the data. But as you see in the top panel, which shows the polarization degree, those are very different between the different models. Unfortunately, we've never had the privilege of high energy polarization before, but as you heard in the introduction, NASA is finally launching the first X-ray polarimeter, which is called the Imaging X-ray Polarimetry Explorer, or XP. Our launch date is the 9th of December, so just over a month from now. We'll be operating in the 1 to 10 kV band, and it is a small NASA mission, which means we have about 2-year lifetime, but can be extended to more if we're successful. So we have been working very hard trying to prepare for this very unique data set that is coming our way. And of course, our challenge was that we have no idea whatsoever what to expect for the X-ray polarization of Blazars. So we had to be a little bit creative into taking what we do know and converting that What we do know is the optical polarization, of course, and we need to convert that to what IXP will be observing in just a few months from now. So this is a work I did with Lawrence Pearson, who is a graduate student at Stanford, where we used what they call multi-zone jet models. So what you're seeing here is a cross-section of the jet, and it's made up of smaller emission regions, each with its own particle energy distribution in its own magnetic field. So if you let the simulations run over time, what you get as the emission is the sum of all the zones, and then the polarization is about the maximum you get from synchrotron radiation, or the theoretical maximum you get, which is about 70%, divided with a square root of n, where n is the number of zones that contribute to the emission. So if you, for average jet parameters, you can run the models and the simulations, and then you can get how the polarization degree changes across the synchrotron spectrum. So then for individual sources, if you know the optical polarization and you know where the peak of the synchrotron emission is, then you can scale your simulations to give you what is the expected X-ray polarization degree, which is what you see here. So that's in the y-axis, and the x-axis has the X-ray flux of the source. The red dashed lines are the IXP sensitivity for different exposure times, which are typical would be around 100 kilosecond. So as you can see, we should be able to detect a few sources, at least a few sources, relatively easy. Of course, the ones are more relevant to what I've been discussing is basically the ones with black. That is the sources where the X-rays are in the high energy component of the SED. So in our models, we're using Synchro-Compton, and scattering typically depolarizes the emission. So that's why all of these sources are systematically lower than the green points or the blue points, which are different classes of Blazars. Now, if we're not looking at Synchro-Compton, and we have some hadronic process, and in this particular energy range, proton synchrotron is the dominant one, then we expect all the black points to be about 3 times higher than what you see here. So a few of them will find themselves in the easily detectable zone by IXP. So we've built our program in a way that we should be able to place some very interesting constraints on this emission processes, even from the first year of IXP observations. So of course, I'm not expecting that we'll see something different. I hope I'm wrong, but my money is on Synchro-Compton, and there are a few reasons for that. One of them is that we recently looked at what are the energetic requirements of these proton synchrotron models. So we basically asked the question, is there enough energy I can extract from a black hole so that all of my high energy emission is explained by a proton synchrotron model? So basically, we estimated what is the minimum jet power you need, and we compare that with typical energy estimators we have from supermassive black holes with jets. What I'm showing you here is a comparison, what we call the Blackmore-Snaik, is the power that comes from the Blackmore-Snaik mechanism. This is the mechanism where you directly tap into the spin of the black hole, and basically the maximum energy you can extract. And the equality is the black solid line. The dashed line, where most sources seem to cluster, is 2 orders of magnitude higher. So basically what this is telling us is either our understanding of jet energetics is wrong, or there is simply not enough power in the sources to have all of their high energy made by proton synchrotron, which is of course a testable prediction in just a few months. Of course, everything I've discussed so far is limited to whether you have a purely leptonic or a purely hadronic model. But since the neutrino association, there is a class of models which are hybrid, we call them leptohadronic models, and they're beginning a lot more popularity because of course they're a lot more versatile, and they've been they have shown to be ways to explain, let's say, this neutrino event. And this is one of those models that I found particularly interesting. Basically, all of your electromagnetic output is dominated by leptonic processes, and you have a subdominant proton component where it only manifests itself in the neutrino emission, of course, or at very high energy gamma rays, which are absorbed during propagation from the source to the observer because of the extragalactic background light. And in the X-ray regime, only for this particular class of blazars where, as you can see, this lies in the transition region between the low and the high energy component, where the leptonic emission, which you see in the orange, is minimal. Which is, of course, perfect for us because this is exactly where IXP will be observing. So it'll be very interesting in trying to measure this component, if, of course, it exists. So we've gone out of our way in trying to find sources where we can actually do this experiment. And of course, we started looking at sources we've already identified as good candidates for IXP. So this is the source called 0716 plus 714. And what you see at the bottom panel is a combined Swift and NuSTAR observation. Those are X-ray satellites, where you can see the transition between the low and the high energy component. And we've modeled that with this multi-zone jet models. So what we find is happening is basically as you move as the synchrotron component dies down, you get emission from fewer and fewer zones, which gives rise to polarization. But the Compton component, remember again, we're dealing with the Synchro-Compton model, that starts to dominate the emission. So the end result is this green line, which shows this steady decline of the polarization degree across the IXP band, which I show you with the magenta, the vertical magenta lines. So if proton synchrotron is dominating in this band, there is absolutely no reason why you would expect a change. It should be just a flat line across the XP band, which is something that we can actually test for, something that we can actually go and try and measure. We recently discovered that the other good candidate for XP also shows this transition region. This is an XMM observation. That's another X-ray satellite, which we got very recently. And you can see this shown in the blue points. You can also see this kind of transition region there, but I haven't had the time to model this yet. And of course, we've already done the modeling of the neutrino candidate. And actually, lately, we've transitioned to not just looking for a best fit model, but rather an ensemble of different models so we can better understand what exactly is happening during this transition. But also in this case, we see kind of a decline of the polarization, although it's not as prominent as it was in the first case. I have to be honest with you. We don't know whether this experiment will be possible with IXP. This is something we're still trying to figure out now. But even if it's not possible, then you don't have to despair just yet. There is, IXP might be the first, but it's definitely not going to be the last. So roughly after we finish our mission, this EXTP is going to be launched. This is a Chinese-led mission, which is basically 3 IXPs put together. So you have a lot more sensitivity. And we've already put out a white paper for NASA's next mission, which is going to be the X-ray polarization probe. And of course, there is eAstrogam and Amigo. eAstrogam is led by Europe. Amigo is led by the US. And this is a mission in the MEV range, which is also something that we've never had a polarimeter in that range. And there's a few interesting hadronic signatures in that range that those missions can look for. So I hope I convinced you by far now that the astrophysical jets are very exciting laboratories, and polarization is relatively underexplored, but is really a powerful tool to understand these processes. We still have a lot of questions, but like I said, in just a month from now, the IXP will open up a new window to the universe, and hopefully a lot of the questions that we have now will soon be answered. So 2022 will definitely be a very exciting year for those of us working in jet physics. Thank you very much.
Thanks, Yannis. Do we have any questions? So for people who are on Zoom, you can raise your hand, and for people in the room, you can raise your actual hand. Yes.
Why don't we see the other jet in Blazars if they're not perfectly aligned with the line of sight?
Well, this has to do with the fact that they're relativistic. So a lot of special relativity effects come into play, where the jet that's coming towards you, it gets boosted in luminosity by, basically the velocity of the jet in cubed. And the jet that's going away from you, it gets dimmer by the same factor. So even if you have a mildly relativistic jet, you end up in the contrast of, 10,000 to 1. So it's there. We just don't have, instruments don't have the range to detect that. Also, it's a matter of resolution, because if the jet is aligned towards your line of sight, then the other one is basically hiding. One jet is hiding behind the other. So it will take like a very extremely resolved image to see something. But we do, like for example, in M87, which I said it's kind of in the middle, we have hints of the counterjet. So we're getting there.
So they're just, this higher energy emission is redshifted down. That's just too faint for us to see with radio telescopes.
It's more relativistically boosted than redshifted, because that happens locally. It's not part of the expansion of the universe. But yes, you're correct.
Jim has a question on Zoom.
Yeah, I just had a number of questions and comments. First, I just wanted to say how much better this data looks than when we started looking for back in like my 1996 Whipple paper, when we saw the first perhaps correlation with the optical polarization and stuff like that in Markarian 421. I mean, this is just amazing, your multi-wavelength data, how rich it is. But then it's also depressing because you get all this information and it's still hard to parse. But that was my first comment. The other comment is, I just want to say that I think the ice cube neutrino is a red herring. There are just so many things wrong with like photopion production. I mean, the timescales for accelerating the protons to high enough energies just does not match the timescales. The spectral variability you expect from the synchrotron giving you the gamma ray emission, it doesn't make sense. So, I mean, politically, it's very nice, but I think it's a red herring. That's another comment. And I have one more thing, but I'd like to hear your opinion on that, your candid opinion.
Well, let me go on the first comment that you made. And basically, this is something we've been discussing with Alan Marcer, that this goes against us. So the more data we have, the harder it is to actually fix a model too. He was telling me that his very famous paper on the shock in the jet would not have worked with today's data.
Right. That's a very good point. Yeah.
So on the other side, I have to also admit that I don't believe the neutrino association as well. We've been trying to figure out to basically So one of my problems is that there's never been another neutrino association since then. There are a couple of other plausible associations, but I think people are just trying very hard.
Yeah, the energetics, like you say, I mean, before IceCube was built, I tried to argue that, look, you're assuming the source is as bright as Markarian 501 was at its brightest all the time to get a measurable flux. So I'm pretty sure the energetics are a problem. So
maybe I can share something in that paper. We actually did the exercise of trying to estimate what the neutrino flux will be. So just give me one tiny second.
Yeah, I'd like to see that.
I'll get you that plot. Now I cannot find where the paper is. Oh, okay. I think I got it. Okay. Yeah, so here it is. So basically with proton synchrotron, you are nowhere near the IceCube sensitivity. Apart from this source here, which might be, we actually asked people to look whether there's something in that direction, but they never came up with
right. And there anything. I see there are 2 order of magnitude tick marks on the axis. Yeah, I that makes sense to me. And I'm sorry, I just had one more quick question.
Oh, please go ahead.
Sneak in because this is so interesting to me. It's been a long time since I thought about this, but you know, you talked about this multiple kind of zone, like the different polarization regions that can kind of come into play. And I've heard Alan Marsher talk about this too, and I talked to him about it at AAS meeting. What's really fascinating to me is and you've probably done this. So I think the evidence is that the high energy gamma ray emission comes in very close to the jet. I think the jet could be decelerating even in that region. And as the jet decelerates and the 1/gamma angle changes and sweeps through all of these polarized zones, you have the effect that you're looking at different numbers of zones, but you're also looking edge on from the standpoint of relativistic aberrations and stuff. So if you look early on with a decelerating jet and this multi-zone kind of picture that you're showing, I guess, would it be that you would expect to wash out, you're expecting to wash out the polarization signal because you're averaging over more regions, or how does it work?
That would, so when we're running these models, we're assuming that there's a constant velocity. And the reason is basically pragmatic. Like it gets very hard to keep track of what's happening, especially when you go to the high energy and try to estimate what's the inverse Compton polarization, because each of these zones is basically self-contained. Photons are allowed to roam free. So that's why you get also a depolarization from the from inverse Compton scattering, because it sees photons from adjacent zones, and it will be almost impossible, the way at least it's set up right now, to track all of this if the jet is decelerating.
I see. But
so that's one limitation we have for the high energy part.
It's interesting though, because where the jet is decelerating near the very central engine, I would think there's a lot of energy available there also to satisfy, you know, some of the energetic constraints on things. So I don't know. I think that would be like Henrik. I don't know if he's here, but he one of the early papers on M87, and this flip flops back and forth. But it really looked like the TeV emission, for example, was well within the synchrotron self-absorption region, and the radio was really coming further out. So I think deceleration would be cool to see if there's a way to calculate signatures. I think that would be neat.
So this is, I mean, first of all, I fully agree that this is as the picture we've come to. We've done the cross correlation between all three bands, radio, optical, and gamma rays. And this is what we see typically. Optical and gamma rays are coming very close together, and then radio is typically lagging by maybe 100 days even.
So that's that pattern is holding true or is reinforced by subsequent observations. That's interesting.
What we did a paper recently where we actually tried to find this deceleration in the radio regime. So basically looking at how relativistic effects change with different frequencies. And we couldn't really find, we mostly found jets that have a constant velocity, at least between 4 to 37 gigahertz. There was only 3C279 that showed a very strong decelerating pattern.
Interesting. So as you go to higher frequencies and you go closer to the source, you could see evidence for higher velocities in 3C279.
Yes.
That's very neat. That's very cool.
We actually had also ALMA data, so we went up to 340. And in some cases, I can maybe link the paper to the chat. But especially in 3C279, we actually managed to find the band that EHT reported in the paper just a month before us, basically. And then we saw the jet, after it reached some maximum, it started decelerating.
Cool.
But yeah, we don't really see that much deceleration in the radio in the other sources.
But one may really expect the deceleration to have already taken place by the whatever these Compton rocket kind of arguments are, just the rapid deceleration within the self-absorption radius. So anyways, okay, very cool. I'll stop monopolizing the conversation, but thanks for the nice talk.
Do you have any more questions? I had a short question. So when you looked for correlations between optical flares and also how the optical flares have a change in polarization in correlation with gamma ray activity. So you showed that for all classes of blazars, it still holds that these flares are coming at the same time in optical and gamma rays. And then you mentioned that you found about 20% of gamma ray flares that were orphan. Is this appearance of orphan flares also the same for all classes of objects?
Oh, that's a good question. I don't exactly remember.
Okay.
But maybe our statistics were not great to tell. But I definitely don't remember there being a difference. That would have been very, very interesting. Yeah. But I'm not exactly sure why you cannot remember what happened. Why we had on an average instead of looking, because we actually looked at individual classes and the orphan flares in some papers, but for this particular one, I don't remember exactly why. I don't think there was a difference.
Yeah, I guess, yeah. I mean, if there was something obvious, you would probably.
There was there was a kind of overrepresentation in the sources that don't show the correlation, and those tend to be the high sequential peak sources. But we think this is also an observational artifact because those will have more contribution from the host galaxy because they're more nearby, which tends to kind of dilute the variability of the sources.
Although I think for Mercurian 421, when we were staring at it with Whipple and staring at it with optical telescopes, we didn't see good correlations with the optical at all. And that was when we were really taking high temporal density data in both bands. So you may, that's anecdotal, but it fits with what you're saying, that the high energy peaked objects don't show the correlation.
Yeah, and it also looked like in the light curves that you showed at the beginning, there were, it looked at least that there were sometimes changes in polarization that did not map with gamma ray activity in the, I think it was 3C454 that you showed. Yeah, so there is some structure on the polarization light curves that
For
may
example,
or may
here,
not. Yeah.
or here. I mean, we don't know where these things come from. There is still a lot, really a lot to learn. But this might look also in contrast, because these flares are pretty much gigantic. If you look at the full light curve, basically what you see here is 4 times brighter than what happened in 2013. So if you put them side by side, one of them doesn't really look that, this one that will not look that, you know, impressive either.
Yeah.
So you really have to go in and, you know, look at individual events, and that just, we're working on it, but it takes really a lot of manpower and effort to do. That's why you see also there's a lot of, you know, we published in 2020 some that happened in 2014, right?
Yeah. Any other questions? So if anyone wants to, Yannis said that he could stick around for a little bit. So if anyone wants to speak with him, maybe just send me an email and I'll arrange kind of a Zoom session or something like that. And so Yannis, maybe I'll stop this meeting now, and then I'll set things up and I'll go back to my office, and then we can meet maybe in 10 minutes.
Using the same link, or
I'll send you a new link.
Okay, great.
Okay.
So thank you for having me.
Thanks, Yannis.
Thanks.